This is our introduction to our rotation unit. We're going to start by talking about the concept of torque, leading into look at statics. So rotation really incorporates all the things we've learned in mechanics so far. Newton's first law, which is what we're starting with, rotational inertia, Newton's second law, and the conservation laws, all of it. The big difference here between translation, moving along a line through space, circles, straight lines, etc. Rotation means every particle is moving together around an axis. That axis itself might be moving or fixed, and we can combine translation and rotation, but we'll get to that. If you imagine a door, right? The hinges are the axis of rotation, and you need to apply a force to shut the door, but just applying a force doesn't do it. You need to apply it in the proper direction and not to cause it to move so much as to rotate about that axis. And so the way we talk about a torque is basically a force combined with some distance and direction that has to do with causing or not causing, depending on the case, a rotation. So we do this all the time. Every time you open or close a jar, open or close a door, loosen or tighten a bolt, sit on a seesaw. So to create a torque, you actually need four things. You need an axis or axis of rotation, or what's often called a pivot point. You need a distance from that pivot point, because if you're just pushing and pulling on the pivot point, it's not going to rotate. You need some amount of force that's not zero. And you need the angle to be such that it would actually cause it to rotate, right? If you're simply pulling along that R vector or pushing, if you imagine back to that door, if you try to pull it along the door or push it along the door, nothing happens. So by definition, torque is the cross product of an R vector and a force. It has units of newtons and meters. Newton meters is usually how it's described. This is not a joule. The big difference is that a joule came from a dot product for work. This comes from a cross product, which gives us torque, which is a vector, not a scalar. So when it comes to the magnitude, there's three different ways to think about the magnitude. One is just kind of this formula. The torque is equal to the length of the R vector, the length of the F vector, times the sine of the angle between them. You can think of this as R times F sine theta, or in other words, R times the part of the force that is perpendicular to the R vector. Or you can think of it in terms of how much of the R vector is perpendicular to the force vector. This is often called the perpendicular part of R. It's called the moment arm. Any one of them gives you the same result. They are all ways of describing a cross product, but one may make more sense in a given situation. So when it comes to direction of torques, we use what's called the right hand rule. You have to use your right hand, and a couple different ways to do it. But if you point your fingers in the direction of R, so from the pivot point, think of that as your wrist, out toward R, and then you curl them in the direction of the force, you fold them in the direction of the force, your thumb will point in the direction of a torque. It is a cross product after all. So the torque that causes this kind of rotation is that way. Right? Positive torque by convention causes what we call a counterclockwise or positive rotation, and a negative torque causes a clockwise or negative rotation. So an example again, if you want to open a door, so we're looking down from above the door, there's the hinge, and then the arrow points out toward the door handle. If you apply 50 newtons of force perpendicular to the door, distance of 1 meter from the hinge, the torque will be equal to 50 Newton meters. 1 meter times 50 newtons times the sine of 90 degrees, because those two vectors are perpendicular. The direction will be, if you do, it's a little awkward here, counterclockwise, or your finger pointing out at you, or your thumb pointing out at you, positive. Newton's laws are still related here, and we can still think about them. In translation, it was net force equals zero, which meant there was zero acceleration. In rotation, the net torque equals zero leads to alpha equals zero, or no angular acceleration. Now, we sort of skipped over the angular velocity acceleration stuff when we looked at our circular motion unit, so we're going to come back to that in just a moment when we start having angular accelerations. But for now, it's enough to say it's not going to start, stop, or change its rotational speed. In the second law, We end up with net torque as I alpha. More about that later. But the big deal is we're looking at net torque, just like we cared about net force. So if you want to follow along with this part, page 5 in your Unit 6 packet is where this stuff comes from. So if we imagine, right, an object that has, a length of 2 meters, and there are 2 different forces acting on it, force 1, 20 newtons, force 2, 10 newtons there, and the center is at A. We can talk about, and then we've got another one where the same thing, but the forces are in different directions. So we've got 2 different sets of torques we want to try and calculate. So the big thing is that you can calculate torque about different axes. So you can do for both of these around A and B. And so this is the thing that I would ask you to look at before we kind of reconvene. A couple of trickier examples, though. If you imagine a wheel kind of rolling, right, where should the pivot point be? Now, you might think the center of the axle or the middle of the wheel, but it's probably easier to pick a pivot point that is at the edge, that is touching one of the things and giving us a force that we don't really know about. If we apply this force horizontally, to its rim, it's easier to think about this in terms of not necessarily RF sine theta, because that's a little bit difficult, but it's easier to think about this in terms of, well, the moment arm in this case, right? Because there's the R vector that we care about now. It's just the amount of R that is perpendicular. That's a short distance. That's an easier distance to figure out. We know that the diameter of the circle is 20 centimeters. We know the height of that is 4. So we can pretty easily figure out what's happening 16 centimeters there, allowing us to figure out the torque, right? So again, this is an example of how sometimes the obvious definition or method, you might want to take a moment. So pages 5 through 7, we're going to be looking at this stuff in packet 6 in class tomorrow. I think so, whenever we meet again. So that's kind of the preview of torque.